So yes, my name is Michele Montanari. I'm coming from the Italian National Institute for Nuclear Physics, where my group has built, which is located in Frascati near Rome, and where my group has built over the year the SCF lab, and SCF stands for this huge list of words, and which is an infrastructure that is devoted to the optical characterization of laser retroreflectors for space applications. So here is we have the list of all the instrumentation that we have. So we have the solar simulator, cryostat, a vacuum system to reproduce the space environment, and an optical table to perform the optical measurement. So thanks to this facility, we started from 2015 to deliver 3 miniaturized laser retroreflectors for Mars mission. So here we have Henry, Larry, and Lara that were installed respectively on a Schiaparelli, InSight, and Perseverance. So by exploiting this Mars heritage, we started to develop new retroreflectors for different solar system destinations and for missions with laser devices to perform laser artimetry or ranging. So here I will introduce the payload that we are realizing for Hera MMX CP11 mission that will fly next year. So let's start with Hera. Hera will be launched next year by ESA to the Didymos binary asteroid, and its main objective are to investigate internal properties of the asteroid and to study the outcome of DART mission. Hera will host a LiDAR and 2 CubeSat, Milani and Juventus. For Milani, which is the CubeSat developed by Tyvak International, we delivered 2 laser retroreflectors arrays that will be installed on 2 phases of Milani. So here we have the picture of the 2 arrays. So we can see that they are identical, and each of them is equipped with 7 CCR, so 7 corner cube retroreflectors, and the front face diameter of each CCR is 7.16 millimeters. So the CCRs are the optical components. They are made of aluminum-coated Suprasil 1 reflectors. And the main frame is instead relies in aluminum with an anodyne surface coating. And the total mass of each array is 5 grams. And here we can see the geometrical dimension. And what I want to point out is that this kind of payload is completely passive from an electrical point of view. So going to MMX, MMX will be launched next year by JAXA to Mars to explore the 2 moons, Phobos and Deimos. And the mission is planned to collect some material from the moons. And in particular, it should deliver a small rover to the surface of Phobos. And the rover will be developed by DLR and NESF, so the German and French agencies. And for the rover, we developed the laser reflector array, which consists of 5 CCRs of ½ inch of diameter, so 12.7 millimeters, for a total mass of 15 grams. Also in this case, the CCRs are made of aluminum-coated Suprasil 1, and also in this case, the payload is completely passive from an electrical point of view. Here we have the picture of the 2 arrays, and we can see that actually the array are 2 different arrays, one with 2 CCRs and the other one with 3 CCRs. And the main frame is aluminum with an anodyne coating. So I decided to add this slide to show how we do select the main parameter of the CCRs, which is the diameter. And this analysis was performed in collaboration with John Degnan. And so we select the diameter of the CCR by looking at their laser return. So for instance, in this case, we wanted to have a ratio between the number of photons that are retroreflected by the retroreflectors over them and the number of photons that are reflected of the surface of Phobos in this case, close to 10. So we performed some calculation investigating different design with different diameters, and we wanted to have this ratio equal to 10 at a distance between the orbiter and the retroreflectors of 30 kilometers. So we saw that with there is a design solution of a flat array of 5 CCRs with a diameter of 12.7 millimeters. We had compromise between the laser return and the geometrical constraints. Here in this picture, we can see the array mounted on the rover, and we can see that indeed we do not have space enough for 6 CCRs. So finally, CP11 mission. So CP11 is an Eclipse mission that we heard about a lot this today, and particularly IM3 or CP11. It's a lunar landing mission that will carry 4 commercial payloads: MPAC, LUSEM, CADRE, and Lunar Vertex that we heard about this afternoon, to Rainer Gamma. So the Earth of MPAC is the MoonLIGHT retroreflector, and the MoonLIGHT retroreflector is a next generation retroreflector that has been designed in collaboration with the University of Maryland. And why it's a next generation? Because the 5 existing lunar retroreflectors are arrays of CCRs. For instance, the Apollo 14 retroreflector is an array of 100 CCRs, or the Apollo 15 retroreflector is an array of 300 CCR, while MoonLIGHT is a single large CCR. And I say large because the diameter of the CCR is 10 centimeters, and it's not coated like the one that I presented for the other missions, which means that light is reflected by the retroreflector thanks to total internal retroreflection. And being a single large CCR is less sensitive to lunar vibrations, which means that could enable millimeter accuracy on a single laser return. Yeah. So MPAC is the name of the payload that we are delivering to ESA. And MPAC stands for MoonLIGHT Pointing Actuators, and innovation stands in the last word, actuators, because the Apollo retroreflectors arrays were manually aligned by the astronauts to point to Earth, while in this case we will have 2 actuators that will point Earth automatically. And so here we have the CAD of the payload. We have 3 main parts. So the TCR housing, which holds the MoonLIGHT CCR, and to the 2 frame, the azimuth frame and the elevation frames that contains the stepper motors and all the electronics to point Earth in both directions, so azimuth and elevation. So this was the last slide, and thank you for your attention.